Awesome. Good afternoon. Thank you, everyone. Excited to be here at PyBay. My name is Mason Egger, and let's just go ahead and get into it, because this is a almost exactly 30-minute presentation. So, by show of hands, who's familiar with this image, or knows what this image is? Okay, it's pretty interesting. So what this is this is a map of our solar system in a geocentric projection. So essentially, Earth is at the center, and this maps all of the celestial objects that orbit the Earth, as it did back in the 14th century, and how they map. So there's the moon in there, Jupiter, Saturn, all of those things. It very much reminds me of the art supplies that we used to have as kids when I was in elementary school, the spirograph things where you would put it in, draw, and get all the really cool, really cool drawings and stuff. It's very beautiful, but it's a little bit complex. It's really complex. Then, in the 16th century, Copernicus put the sun at the center of the solar system, which greatly simplified how we view celestial objects and how we view our world. This allowed for people to start thinking differently about how we think about the laws of nature, how we think about our place in the universe, for all types of different things. Essentially, we got like the law of gravity because of this. This is what inspired us to get to the law of gravity, and we get all of these new discoveries, all these new advancements in science, because what we did is we put the right thing in the center. So it's important to note here that both of these diagrams are technically correct. Neither of these two is an incorrect representation of our solar system. However, for certain tasks, choosing the right frame of reference simplifies what you're trying to do a lot. So for example, if maybe you're trying to send a rocket ship to the moon, looking at moon trajectory, the one on the that side, I can't do left and right on this, is the right one to work with. But maybe if you're trying to send a telescope out to the outer parts of our solar system, maybe you need to be looking at things from the sun and how everything orbits that for a more accurate lineup. So you may be asking yourself, why am I talking about this? We're all building software here. We are ensuring that software is available and scalable for our users is challenging. Scaling any type of software, from order management systems to AI agents, is no different than scaling basically any other application. They're all microservice architectures underneath the hood. And at the end of the day, because everything on Earth now connects to the internet, everything is a distributed system. I would posit you with that. This is not a new problem, though. This is an old one. We know how to scale distributed systems. We know how to handle it. So scaling AI agents, for example, not a new problem. It's an old one. And we have design patterns to do this. We have event-driven architecture. So a very academic reading of event-driven architecture is a software design pattern where components communicate by producing and consuming events, allowing for loose coupling and asynchronous processing where systems react to state changes or occurrences rather than direct method calls. Pretty straightforward example. But let's walk through a system that's built on top of using events. And we're going to do this with a payment processing system. So first we have our payment system, which when we send our payment, it is then sent to our payment ingestion service. This service initiates the payment for the users and validates that the basic payment structure is correct and all of that. The payment ingestion service then publishes the payment as an event onto the message bus. Now, if that publishing doesn't work, we'll need to retry that logic to make sure that it eventually does work. And if the payment fails the validation, well, then we need to send it back to like a dead letter queue until someone can come back and fix it. And then we have to make sure that we're constantly checking that to make sure there's no stuck payments for this. Then our payment system service basically subscribes to a message bus for the payment processing system. So it sees this event and it processes the payment basically via temporary auth. So if you go out to a restaurant, you do a temporary authentication for that. Then the payment processing service writes this to a database, updating it later if, say, someone leaves a tip or something. Very standard. Any fail write, though, basically results in an entire loss of your data. So if you can't make sure that this write works, you lose the data, and someone got a free lunch, which sounds good to me. Throughout the day, all of your payments accumulate, and at the end of the day, you send it to a batch processing job. Also, if you've never worked in payments before, this is kind of enlightening. If you do work in payments, I'm sorry for the oversimplification. It's a talk. Don't hurt me for it. But it sends to the end of the day. The data is then aggregated and sent to a cleaning service for each payment type, and then the database is eventually updated. And some of you might be sitting here looking at this, and you go, wow, that's a good architecture. Ship it. Love it. And you're right. This is a very standard, typical architecture for a payment processing system. This diagram will work. There are companies that are worth a lot more money than me running this in production every single day. But I might ask you, let's go back to our original hypothesis at the beginning. Do we have the right thing at the center of our ecosystem? You know, we've built all of our applications nowadays, now that we've gone into the microservice architecture, now that we've left monoliths behind. Monoliths are bad, boo, monoliths. I don't agree, but whatever. We now have events at the center of our ecosystem. And if you look at that diagram, there are more parts in that diagram about handling all the potential failure cases than there is actually about the business logic that is making that company any money. I was an SRE in a past life. The worst outages I've ever seen in my life were caused by mismanaged task queues. If you want to ask me about that after the talk, please do. It's not appropriate for stage time. It's really fun. But I do ask you, do we have the right thing in the center? I don't think so, and I'm going to tell you why. What's wrong with this approach? Well, we have a lot of really cool things that we've built in our time as software engineers, and one of them was APIs and API contracts. Event-driven architectures don't have API and API contracts. We sacrificed our clear, well-defined APIs when we adopted the event-driven architecture. Events lack documentation and structure that APIs have given us, leading to ambiguity about which events consume what services and whatnot. And yes, there's the async API spec, but it focuses on the formatting of the messages. It's not an API, it's just what is being produced and consumed. And we all know that developers are great at documentation, right? I work in documentation, or I did up until recently. I'm not worried about anything taking my job. You still have to write the prompt in AI to write the documentation, and you're too lazy to do even that. I'm not worried. So, we have no APIs, we have scattered logic now. All of our applications used to run top to bottom really linearly. It was beautiful, and then we messed it up. Business logic becomes fragmented and spread out across many different services. Instead of having a bug and saying, hey, let me just trace through the code real quick and look what happened, you now have to open multiple files, you're grepping across entire code bases for the event name, and in the worst case scenario, the only way you can find the error is if you actually run the code again, because it's the only way you can witness it. This doesn't sound like fun at all. Visibility becomes nearly impossible because of this, because the state is now in messages and queues across multiple services. Now, every service becomes an ad hoc state machine. Yay! And I know every CS major loves to implement state machines. They love it when they're in college. I say this is because they've never been paged because one went wrong. As soon as you get paged for a mismatched state machine, you really don't like them anymore. Services have local databases now. I can produce and consume messages, and in many cases, there are not transactions between publishing the message and updating your state. So now you have to implement transactions. That thing that databases gave us 30 years ago that we really like, now we have to re-implement all of that on top of it. Now we also have race conditions. Woo! We're getting to the fun part. Everyone's favorite thing to debug at 2 o'clock in the morning when you're sound asleep and the pager goes off. I was an SRE that moved to DevRel. Ask me why. Because of this. So essentially, you have to add logic that ensures all this doesn't happen. Or you can do what a lot of enterprise and companies do. You can just offload it to customer support and let them fix it. It's not a good way to keep customers. And essentially, what all of this leads to, and this will be the most contentious statement that I say of the day, is that we actually built a system that's very tightly coupled. Now, don't throw any tomatoes at me. We are all been told that event-driven systems are loosely coupled. And that's right in some sense. They are loosely coupled, but they're loosely coupled at runtime. Okay, this is why we want to use them, because a system can go down and the other ones can keep functioning. These are some awesome runtime characteristics. This is what we want. But because they are loosely coupled at runtime, people assume that they are loosely coupled at design time, and that is not the case at all. They are actually very, very tightly coupled at design time. So let's do an example of this. Imagine that you're doing a code review with a junior software engineer, and they come in and they say, hey, I refactored all of our service code to make everything more loosely coupled. And you're like, that's amazing, how did you do it? And they go, well, I just changed all of our local variables to global variables. And you're like, why on earth would you do that? And you're like, well, it's really easy. You can add new code, the old code doesn't need to worry about it, and then anybody can write to it and just consume it whenever they want. That sounds absolutely insane. That's exactly what we did with event-driven architecture. Just let everybody read from the topic, it's fine, no one cares. This is the exact same thing we did with our systems. You can just read from it until someone changes the format of the event. That's in 4 companies, 3 orgs over, and you don't know they changed the event. Oh, look, now you have a P1 outage. And because someone changed the event of it. And I saw some people in here wince, and I know it's because you've dealt with this before, and if you listen quietly, you can hear pagers going off. Because it's exactly what happens every single day. So what this leads to is an engineering culture of fear of changing things. Your task queues become write-only file systems. You never update them. You have these Frankenstein, Rube Goldberg, Dr. Seuss machines flying through with topics from 4 years past. You have no idea who's still using it, but you know if you turn it off, it's going to be your problem, and now you have to answer the pager, and nobody wants to do that. So that's what we go with. So now what? What do we do? This is the state we got ourselves in. How do we fix this? we reorient ourselves. We take a step back, and we say, hey, do I have the right thing at the center of my architecture? No. Let's look into it. So let's put the right thing in the center. Well, what is the right thing? I posit to you that it's a new concept called durable execution. And it's not really a new concept, but we'll get to that. So what is durable execution? Durable execution is what we call crash-proof execution. It enables the developer to write reliable software with less effort. It allows them to focus on what the application should achieve instead of trying to anticipate and mitigate every single way that anything could possibly go wrong. This, in turn, accelerates your development. And then basically what ends up happening is your failures are inevitable, but durable execution makes failures inconsequential. What are some of the characteristics of this? What am I going to talk about? Well, durable execution automatically preserves your application state. It virtualizes your execution. It's not limited by time, and it's hardware agnostic. These are what we posit are the 4 primary things of what durable execution is. I'll pause for the people taking pictures. Yay! That's a good slide. So, how does it automatically preserve state? Well, in a typical application, when your application crashes, you lose state. You lose the loss. Sure, a developer could, or you lose the state of the application as it was there. Sorry. A developer could take all this and back it up to a database periodically, creating a caching DB for every single service, and this is what a lot of people do. But this isn't what a developer wants to do. This is not what you're trying to do. You want to solve cool problems, not constantly back everything up to a Redis cache. It's not core business logic. It's a necessary safeguard against failure. This is what I call defensive coding. You're not actually coding anything of value. You're just making sure that things don't blow up. It's defensive coding. It's tedious. Not a lot of people enjoy doing it. In durable execution, application state is automatically persisted to the database by the platform. And this platform maintains the database where this is stored. So basically, your platform maintains the database and all of the orchestration of it. The inputs and outputs of all of your tasks are preserved. This is also the local variables makes them durable. And then what happens is on a crash, the state is rebuilt from the point of the crash using the inputs and outputs that were stored to put you back right to where you were and then continue forward. In the event of a crash, you restore it all. So there are multiple methods for this. We do snapshotting, replay. However you do it, it's identical to what happens. You get your application right to that state before the point of failure happened. And this doesn't mean you don't need databases, okay? Long-term storage, distributed locking systems, these are still very necessary things. But you no longer need a cache for every single microservice because you're sitting there praying that it doesn't break in between the time that the function finished and the time that it wrote to the database. So it virtualizes execution. This is a really fun one. Durable execution virtualizes execution. Execution normally takes place in a single process on a single machine and will immediately end if that process crashes for any reason. Durable execution takes place across a series of processes. It's not just limited to one, each of which can be running on potentially different machines than the one that was before it. And if the current process crashes, durable execution will ensure that the work transparently resumes in the new process, recreating the application state up until the point of failure. And basically, this makes it your failures appear as if they never happened at all. So let's do a visual because I like visuals. So say we have a process. We have process number 1. First task completes successfully. Second task completes successfully. But our third task fails. For this scenario, let's say that we're about to begin executing and a Kubernetes pod just got killed for some reason. It happens. We lose Kubernetes pods all the time. So normally, this would require a full restart of the application. States for A and B are completely lost. But in durable execution, what happens is we create a new process in a new pod. It can either be the pod that was already, we reschedule the pod that went down, or it gets added to another pod that's already running. And essentially, the first task had its state saved, so it was reconstructed and it's not re-executed. The second task likewise does this, and it's reconstructed and not re-executed. But now the third task can complete successfully. If any of the data from A and B was needed for C, it's already there. We already calculated it. We were saving the state of every one of these things that happens. So, but let's go ahead and say, hey, our fourth task process broke again. We're going to say we did something weird and we had another EC2 outage or something. I don't know. Now, we start a third process. The first task is reconstructed, not re-executed. The same for B and for C. No need to redo them. But then finally, the fourth task completes. And this is how our execution was done. And this is what I like to call below the line. So essentially what we get from that is this is the physical representation of our state. This is how things physically happened across multiple processes, across multiple machines. Now we have above the line, which is the logical representation of what happened. This is what the developer will see if they're not very closely anticipating and paying attention to it. And more importantly, this is what your users are going to see. And basically, you have the developer experience or the user experience, and it looks like this happened. All 4 things processed, maybe with a little bit of downtime. One was a little bit slower, a couple milliseconds slower because it had to reprocess on another machine. But from the outside looking in, it looks like nothing ever happened. because we have virtualized our execution. The next thing about durable execution is it's not limited by time. I'm going to give you like 3 seconds. Who here sees the really, really weird thing that you would probably never do? Anyone see it? I'll give you a hint. Who does that and expects it to run? This is 100% valid in durable execution because durable execution is not limited by time. We are maintaining that state. When a timer goes off, the platform can basically deschedule the entire process, and when it's time for it to go back online, it reconstructs the state and moves forward. This is guaranteed to run and will run perfectly and will take up 0 CPU cycles while it's doing it. Pretty neat. It's also hardware agnostic. So for many years, if we wanted to receive any types of fault tolerance, we needed really expensive hardware. Who's ever actually worked in a data center and had to buy like really expensive fault tolerant hardware? Yeah, it's like getting a mortgage every time. It's great, except it's the company's money, so it's not you. While this reduces the likelihood of failure, it doesn't eliminate it. It can't guarantee execution will continue on if the failure happens. It just tries to like keep you alive no matter what. There's no protection against software defects with this either. So this is only if the hardware fails. This doesn't fix your buggy code or anything. Durable execution requires no specific hardware whatsoever. You can run all of these since all the processes are virtualized, you can run them on different machines in different data centers across the globe. It doesn't matter. If it fails, it will be reconstructed somewhere else. This basically, durable execution overcomes both your software and your hardware failures because of this. So let's go back to our payment processing system, and let's do a durable execution version of this architecture. So the user submits a payment, which is then sent to our durable payment ingestion workflow. The payment ingestion workflow validates the data and then makes a temporary auth. There's no need for a dead letter queue because in most durable execution systems, they have built-in retry mechanisms. So if something fails, it will retry until eventually it succeeds. The failed tasks are automatically retried until they're succeeded or canceled. Intermittent failures like network outages don't really affect it because these retries happen along with database writes, all sorts of things. And obviously this can be configured to retry or on something that could never be true, like say divide by 0. So if you get like a real error in there, like a non-retriable error that no amount of retries will fix, then you can configure it as you would like. But in reality, in distributed systems, most of our errors that happen on a daily basis are network errors, and most of them resolve over time by themselves. That's just the reality of it. From there, there's no need to write to a temporary database, accumulation data. I cannot say that word, accumulation database. As the state is preserved, it's just a durable timer that's used to send it at the end of the day. We can now send a batch process for cleaning our processing, getting the result, and then write back to the payment. I'm not going to keep saying accumulation database. Hey, I did it, yay. And then we have a cleaning service. This is what that original architecture was, but redesigned in durable execution. Seems a little bit simpler, don't you think? A lot less arrows. I'll tell you right now, as someone who wrote this presentation, this was a lot easier to animate than the other one. So, do you want to know a secret? It's all still events under the hood. It's all still event-driven and event sourcing. But what we've done is we have moved the complexities out of the platform layer and into the application layer. And this is something that's really neat. So we see this happening more and more across the industry every single day. We see jobs like full stack developer, where the engineering needs to know front end, back end, databases, QA, CI/CD, cloud computing, security, documentation, project management, and they're looking for a college new hire with 35 years of experience. I'll tell you what they're really looking for. Rainbows that fart unicorns. That's what they're actually looking for. These things don't exist. So we're seeing ourselves kind of start to abstract some of these concepts out into the software layer to make our life a little bit easier. And it happens. It's called growing up. We do it. This is actually, if you look at the history of software development, which is something that they don't teach in college at all, but it's something that I've always been super fascinated with because the vast majority of the really cool stuff that happened in software engineering, minus AI and the internet, happened before I was born. So I don't know about why these decisions were made. Why do we do things the way that we do? Why is the network stack designed the way it is? If you've ever watched Dr. Russell Kirk-McCusick's thing on what happened at the Berkeley and BBNN story, it's a really fun one. I recommend you go look it up. But basically, we have the evolution of our software industry. We have a long history of abstracting away complexity from the user. Fortran gives us mathematical operations, so we don't have to manually move things across registers and shift things. Algol 60 and Pascal gave us the if-then-else, so we're not blindly jumping through our code. And if you are, may God have mercy on your soul, because that's going to be awful. Lisp gave us memory management and the garbage collector. Simula and Smalltalk abstracted data away and gave us object-oriented programming, and the list goes on and on. What I think is that durable execution is the next step. It's the next step in our evolution of software, and what it's doing is it is abstracting events, this entire complexity of that we need to manage events into the software layer where the developer doesn't have to worry about it and the platform can handle your queues and making sure that these things line up and all of that. So how do you get started with durable execution? There's a ton of different projects and resources that do it. So the one that I currently tied to and work for is Temporal. We're kind of considered the category creator in this market. It's MIT licensed. This is a code-oriented, no DSL, no DAG-based system. There are 7 current SDK languages supported: Go, Java, Python, TypeScript, PHP, Ruby, and .NET, and there's a Rust one on the way. And I think Apple just released a Swift SDK. And it's natively polyglot. So the fun thing is, because all of this stuff is event-driven under the hood, you can call a function written in Go and use that to call a function written in Python, because it's all just going to speak gRPC, serialize the data, send it across, and execute it. And since all of your execution was virtualized across many different workers, it doesn't matter. You just have this fleet of workers sitting there running the tasks, and now you can easily write call Java function in Python, and you can call something in Java when you need to get out to another language, either because you have a legacy system, which we all know we don't all get to write greenfield code, so legacy systems that need to be kept online, or because you're just going to get better performance because you're calling maybe down to a compiled language or something of that nature. There's Cadence. Cadence is Apache 2 license. It's also code-oriented, or it's no DSLs or DAGs. This is actually the precursor to Temporal. Temporal is a fork of Cadence. The people that wrote the Temporal library worked at Uber. They built Cadence. They forked it, and then they went on to create Temporal. Cadence was, and it supports Java and Go with community support for Python and Ruby. You have things like Airflow, which are DAG-based, Apache 2 license. They have durability in it. These are Python-based and highly specific. There's things like DBOS, and the thing goes on and on. So essentially, there's a lot of different ways you can get into durable execution. I would say look into it. It's really neat. A lot of people are using it now for all sorts of tasks. I see people every day that are using it for making sure that payments go through, making sure that monthly newsletters get scheduled, and literally send newsletter, or maybe a payment, like you need to pay your mortgage. Send payment link, sleep 30 days, while 30 years. That's the loop. And it'll run for 30 years, no problems, and no one will ever look at it again. And it's simple code that you don't have to worry about. So, with that being said, it's shameless plug time. I run the PyTexas conference. It will be April 17th through 19th in Austin, Texas. Our CFP is currently open. We just launched our sponsorship prospectus, and it's our 20th year. So if you want to come see me and come hang out in Texas next year in Austin, it's a really cool place, and we'd love to have y'all come out. And with that, that's all I have. I will take questions. Thank you.
So what are the complexities, though, of this with the durable execution? Because I notice, that sleep call would seem to be provided by the underlying library. If you're, or are you basically having to do anything that blocks has to be using that durable execution library?
Yeah. So I think you're asking about blocking stuff, and specifically in the Python async event loop and stuff, or
anything that's
anything that's blocking.
Or anything that's going to basically put that workflow to sleep for some unspecified amount of time.
Yeah, as long as you don't, if you're waiting on input or stuff, because every single one of these workflows basically runs, every execution runs in its own, not execution environment, but event history. It can sit there and wait. And if you need to wait for years, that's fine. There's actually something in durable execution that they use called signals, which is basically the way you can sit there and wait for either a timer to fire or until a signal comes in from the user, and it can just sit there and wait. And it's really easy. You just workflow.signal, and you send in the data, and then the workflow can move on. Because the workflow is not constrained by time, and because the application state is there, it can wait as long as you want. There's nothing there that's stopping it from sitting there and waiting, for a month or for a year until someone decides they want to send that signal.
Hey, great presentation. I'm just wondering, how does versioning work? And if, say, I have a long-running workflow and, oh crap, I screwed something up, I need to patch this, but I can't reset all of these running tasks. Mm-hmm. How does that work?
So I can only speak to how Temporal handles versioning, and there's 2 different types of versioning for it. There's what's called patch versioning, and there's what's called worker versioning. Patch versioning is basically like feature flags, and essentially what you do is all workflows that had proceeded past that point don't take the old path on a replay. All the workflows that are on a new version will take that path on a replay. If you need to be able to actually have them go back in time and take the new path because something messed up, you can reset everything up to the point above and let it continue through. That's patch-based versioning. Worker versioning is actually a lot easier, and it just launched. And essentially, it's blue-green deployments with the processes that run them. So only new workflows that are running on the new path will go to the new workflow, and the other ones will go through the old ones, and you don't really have to worry about it too much. But because there is at least with systems like temporal and cadence, there is a determinism requirement for your workflow code. You can still have non-deterministic stuff in, say, the functions, but the workflows themselves have to be deterministic because they have to be able to reconstruct themselves. Yes, versioning can become an issue, but that's built in. And you get that more out of replay-based durable execution systems than snapshot-based durable execution systems. Some people like to use the WASM, and they'll try to do snapshots and basically keep an in-memory thing of everything as they're doing it, and they apply that in. But the problem with snapshot-based is that you can never go back in time. You can never change the route. You're stuck with what that is for eternity. Whereas a replay-based system, which essentially downloads all of the function calls and stuff, and then basically reruns the workflow code with that variables to put the thing back in the original state, is a more easily versioned approach.
You said that under the hood, it's still an event-driven architecture. Mm-hmm. So what is sort of the minimal infrastructure you need to have running in the
Depends on the size. So so Temporal is MIT open sourced, always will be forever. Everything that's in our commercial offering is the same thing that's on the open source version. There is a single binary for development that you can run, and we call it the dev server, but it's actually a very load-bearing name. It can do a lot. So if you're doing this for prototyping, if you're doing this at home labbing and stuff, I run a lot of temporal stuff in my home lab, and I'm fine with a single binary, and it just runs a binary and then a running worker that executes it. As you scale up, you need larger and larger infrastructure. There's Docker Compose. You can do it with Docker. Temporal has Helm charts that allow you to just deploy it in a Kubernetes cluster. And then as you get to very large scale things, this can scale very large. If a lot of times people will self-host and then they will try to move over to the paid option because it's just cheaper at the long run. But as you get to production grade, it gets larger and larger, and the Kubernetes cluster can become quite large. And then obviously a database that is ridiculously available because all of this is persisted. Yes, sir.
Question, just curious, there must be some contract between the infrastructure and the individual steps. So for example, I'm assuming, let's say I have a step and it's updating a database somewhere or doing something. If that step fails, how do I know whether or not the actual persistent change was made or not?
Yes, typically in durable execution systems, you have to those are what we'll call those tasks for the sake of not mixing other people's terminologies together. For those tasks, it is highly recommended for anything that mutates state, you make sure that task itself is idempotent. So the onus of making sure that the idempotency happens is on the developer, not on the platform. And if it could have been done in the platform layer, it would have been done. But the problem is idempotency usually relies on the downstream service. Whether or not, databases typically have idempotency keys. There are some really interesting APIs that have idempotency keys, and they handle it for you. But if they don't, then you have to implement it. So because you're right, we could get all the way through the execution of a task, the network could fail, and then it doesn't make it back to the service. So that's why activities are this is not exactly once execution. This is at least once execution. We can ensure that we will at least run it once, but it's still exactly once is just as hard as it was all that time ago.
So you mentioned for task failures, task C failed and then it retries. What about if there's a bug in the code, and how do you communicate that back to the developer? And now there might be thousands of tasks in this error. It's not a failure, it's an error state that you want to correct.
Yeah, so that's a great question. How do we check to see if say there's a bug in the code? This is a really fun one to do. So what you can do is you can actually update the code and fix the bug, as long as the prior executions don't need to be reset for it. And yes, if you have tens of thousands of executions running, you're going to see tens of thousands of workflows that are hung in a retry loop. But what will end up happening is you can fix the bug, redeploy it, and because you already have all of that previous state, you can then redeploy that code. They'll all eventually pick that new code back up and continue on the execution. So even a bug in your code doesn't require a restart as long as you don't need to change the results from the previous states. Now, if you're doing something that's really time sensitive, where maybe you're getting stock prices or something, and that has to update quickly, then yeah, that would probably require a full reset of the workflow, because it's something that hangs for a long period of time isn't a good thing. But if you're doing simple database queries and gets and stuff, none of that has to be retried because there's nothing in there. The state did not change in that amount of time. So you would just fix the code, redeploy the worker, and then the workflows would all pick it up and continue execution on. So even bugs in your code don't cause application crashes or failures anymore. You can still reuse the state that was already executed in production. Thank you.